If someone were to ask you for a fourth root of 16, well, you can say that the fourth root of 16 is going to equal to 2. Or someone could also came along and say that, well, if the question asks for a fourth root of 16 like this, we actually have to answer the negative number as well. We have negative 2 as the answer as well, because if you raise these guys to the fourth power, then I'm going to get 16. And indeed, these are fourth root of 16. However, these two guys are the fourth root of 16 when we talk about 16 as a real number. If we think of 16 as a complex number, some complication will happen. Let me actually go back up a little bit to the theory here. Okay. Now, one nice thing about complex number is that when we talk about a complex number, it will always have n distinct nth roots. So if we want to find the fourth root, there will always be 4 of them. If I want to find the fifth root, there will always be 5 of them. If I want to find, let's say, like 1,000 root, if I want to find 1,000 root, there will always be 1,000 of them. Now, to find all this root, we will start off with the first one. If I want to find the nth root of r cis theta, well, one of them is going to be the nth root of r cis theta over n. Now, the reason why this definitely serves as the nth root is that if I raise this guy to the n power, if I raise the nth root of r cis theta over n to the n power, I'm gonna get, let me see, the nth power of n root of r is going to be just r, and then this is CIS. And then I multiply n to the angle here, so I get theta. So then, the nth power of this guy is going to be just r cis theta. So this guy is definitely one of the nth root of r cis theta. Now, how do I find the rest of them? Well, one thing we see earlier is that when we talk about the root of a complex number, they will kind of spread out in the complex plane. So once I find one of them, I can find all the rest by seeing that they will spread out, so the angle between each of these guys are gonna be the same. So once I knew that this pink guy is, let's see, the nth root of r cis of theta over n, I knew that all n of them are going to spread out, so all these little angles here are gonna be equal. So the angle for this one, so the green angle here, let me actually highlight that. The green angle here is going to be 2 pi over n. So then if I were to find this next guy, the polar coordinate for this guy is going to be the nth root of r cis of pi over n, theta over n plus 2 pi over n. So that is my next guy. And if I were to find the next one, I just have to keep adding 2 pi over n to my angle here. So it's going to be, the nth root of r cis of theta over n plus 2 times this guy, which is going to be, let me just write this as 2 times 2 pi over n. And this will keep going. And because there is going to be n of them, so there's going to be n minus 1 such green vectors here. So the last one is going to be, let me see, the nth root of r cis of theta over n plus, there's going to be n minus 1 of them, so the last one is going to be n minus 1 times 2 pi over n. Okay. Now then, well, instead of writing all these n minus 1 vectors, we usually write it as a shorthanded because, well, we can kind of see that all these vectors come from theta over n plus 2 pi over n times 1. So this is, let me see, this is 1 times 2 and so on to n minus 1. So all these guys, I can write them, I can actually add this fraction. It's going to be theta plus 1 times 2 pi, theta plus 2 times 2 pi, and so on until theta plus n minus 1 times 2 pi. So it's going to be theta plus 2 pi times k, where my k run from 1, 2, 3, 4, 5 until n minus 1. And then the denominator is going to be n here. Now, if you were to notice two things, if I actually keep going, so if I forget to stop at n minus 1, what I'm going to end up having is going to be the nth root of r cis of theta over n plus n times 2 pi, n times 2 pi over n. Notice how the n will cancel out and I'm going to get 2 pi. But if I add 2 pi to any number, it's going to be, if I add 2 pi to an angle, it's going to be the same thing. So the purple guy here is just going to be the same as the pink guy, the first primitive nth root that we see earlier. So this is one thing. If you keep adding, it will actually you can kind of see here as well. If you keep adding 2 pi over n, it will eventually come back up to be the pink vector again. And also, we can kind of combine these two things together as well. We can combine these two things together. But instead of starting k with 1, I'm just going to start k as 0 then. Because if k is 0, then it's just going to be theta plus 2 pi times 0, which is just theta. So sometimes in the textbook, they will say that all the nth root of r cis theta are going to be the nth root of r times cis of theta plus 2 pi k over n, where my k runs from 0, 1, 2, 3 to n minus 1. And this is because when my k is 0, this is going to be the same as the primitive root anyway. So now let me actually go back to the example earlier and continue that. If I want to find all the fourth root of 16, then I can do this by writing 16 as a in polar form. So this 16 here is going to be 16, 0. So it's going to be 16 plus 0i. It's going to be a vector of 16 unit long. Cis of the angle here is going to be just 0. So the fourth root for this guy is going to be the fourth root of 16, cis of 0 over 4. This is going to be my primitive root, and you can kind of see that this is going to be 2 cis of 0. 2 cis of 0 is going to be just 2. So this is one of the root that we see earlier, and we see that 2 to the 4th power is going to indeed be 16. Now to find the rest of them, so my pink one is this guy. This is just 2. The other 3 will form equal angle between them. So this guy, this guy, this guy. Because there's 4 of them, so each of these angles is going to be just 90 degrees. So they are going to be, so let's see, this guy is going to be the fourth root of 16, cis of 0 over 4 plus 2 pi over 4. Now this is going to be, let's see, 2 cis of pi over 2. This is going to be just 2i, and that's going to be this vertical vector here. If I keep going, I'm going to get the fourth root of 16 cis of 0 over 4 plus twice of 2 pi over 4, which is going to be 4 pi over 4. This is going to be 2 cis of pi. So that is going to be another green horizontal vector here. This is going to be just negative 2. And this is again one of the real roots that we find earlier. And the last one is going to be the fourth root of 16 cis of 0 over 4 plus 6 pi over 4. And that is just 2 cis of 3 pi over 2. 3 pi over 2. And this is going to be negative 2i. And this is one of the downward looking arrow that we have here. So this is going to be all the fourth root of 16. So all these, so if we raise 2 to the 4th power, then you're gonna get 16. If we get negative 2 to the 4th power, I'm gonna get 16. If we raise 2i to the 4th power, let me try that. So let me see, 2i to the 4th power is going to be I raise 2i square and then square it again, 2i square. This is going to be 2 square, which is 4 times I square, which is negative 1. So I'm going to have negative 4 square, and that is going to equal to 16. So this is indeed one of the fourth root of 16. Now, for the next one, I want to find the second root of negative I. Again, well, if I want to find the second root of negative I, so funny thing, when we define I as the root of negative 1. So at some point, people were wondering, if I want to find the root of negative I, is this gonna end up being a complex number, like a super complex number or something like that. But it actually turns out that if I want to find the second root of negative I, it will actually be just another complex number. So now let me actually first convert this negative I into its polar form. So negative I would be about here. So this is 1 unit long. And then the angle here is going to be negative 90 degrees. So this is going to be 1/6 of negative pi over 2. So the primitive root for this guy is going to be the root of 1/6 of negative pi over 4. So this is my primitive root. So if you were to look at that, it's going to be a unit vector. And the angle here is going to be negative pi over 4. So it's about right here. Now, there should be two second root of negative I, and they should spread out in the complex plane. So the other one is going to be this green vector here. So it's just gonna point in the opposite direction as my pink vector here. Or if I were to use the formula, that's gonna be negative 1/6 of negative pi over 4 plus 2 pi over 2. And this is going to give me, let me see, this is going to give me 1/6 of 3, wait a minute, 3 pi over 4. So that's going to be the other second root of negative I. Let me actually make this green. So it kind of coincides with with the color of the arrow here. And we can kind of see that the 3 pi over 4, this angle here, this is kind of the purple angle that we have here as well. Okay. So for the last example, I'd like to find the fifth root of 3/6 of pi over 4. So this is already in polar coordinates. So the fifth root, the primitive fifth root of this guy is going to be the fifth root of 3/6 of, let me see, pi over 20. Okay. So this is going to be my primitive root, and to find the rest of them, let me actually just write it out. It's going to be the fifth root of 3/6 of pi over 20 plus 2 pi over 5. So that's going to be my next one. And to find the rest of them, I'm just going to add 2 pi over 5 to the angle here. So, let me actually just write them out. It's going to be 6 of pi over 20 plus 4 pi over 5. And then the next one is going to be, let's see, pi over 20 plus 6 pi over 5. And then the last one is going to be the fifth root of 3/6 of pi over 20 plus 8 pi over 5. So here are all the fifth root of 3/6 of pi over 4.